Welcome, and let's unpack this. Today, we are literally diving deep into hydrostatics, the physics of fluids that are just sitting still.
Resting fluids, exactly.
And if you've ever looked at a massive cargo ship and wondered how it floats, or, how a giant telescope can use liquid metal to make a perfect mirror.
Or even just why a raindrop is always a sphere.
Exactly. Then this deep dive is for you. We're working with a really fascinating stack of source material today that honestly, it reads like a physics masterclass. It guides you from the absolute basics, like what is a liquid, all the way up to some really complex microscopic stuff like surface tension.
Our mission today is to really get under the hood of all that. We want to understand the fundamental mechanics and some of the key paradoxes of static fluids. The goal is to distill these sometimes complex derivations into knowledge that's intuitive, something you can actually use.
Right.
So we'll explore how pressure behaves, both under gravity and when you spin it around. We'll figure out the exact shape a spinning liquid takes on and why.
And then we get to the really small scale stuff.
Yeah. Then we'll look at how the forces between molecules create surfaces, which is what lets droplets form in the first place. And fascinatingly, how it allows trees to pull water hundreds of feet into the air.
Mm.
This journey, like you said, it really explains everything from the crushing pressures in the deep sea to the tiny microscopic actions that are critical for weather and, well, all of botany.
I love that scope from the huge colossal scale of ocean pressure fields right down to the capillary action in a single leaf. It's the whole picture. So let's start at the very beginning. We need to ground ourselves in what we're actually talking about. Okay, so the first distinction we have to make is the most basic one. What physically makes a liquid different from a solid? Because I think we often treat liquids as just, soft solids, but the source material is really clear that there's one single concept that defines the difference.
And that's shear force.
Shear force.
That's the whole game. Understanding that is the key to all of hydrostatics.
Right.
Think about a solid, a brick, or a metal bar. It has an internal structure, right?
Sure, a crystal lattice or something like that.
Exactly. So if you apply a force sideways on it, tangentially, we call that a shearing force. You're trying to bend it or deform it. The solid resists. It has these strong internal sources, we call them restoring forces, that pull it back to its original shape.
Like when you twist a ruler and let go, it snaps back.
Precisely. You're fighting against its internal structure. Now, try to do the same thing to a liquid. If you apply that same tangential shear force,
The layers just slide.
the layers just slide
Yeah.
freely. There's no elastic resistance, no restoring force trying to snap it back into shape.
It can't bend water. You just displace it. It moves and then finds a new flat equilibrium.
And that's it. That absence of restoring forces against shear or torsion, that's the true physical definition of a fluid. And this one fact, this lack of internal structure, it has a huge consequence that basically forms the foundation for everything else we're going to talk about.
Which is what?
It means that when an ideal fluid is touching a wall or a piston or any boundary, the forces it exerts can only act in one direction,
And that direction has to be.
perpendicular to the surface. We call them normal forces. Think about it. If there was any tangential force, any shear force at a boundary,
The fluid would have to move. It would flow.
it would flow instantly to
Yeah.
relieve that stress. And since we're studying hydrostatics fluids at rest, we operate on the assumption that the fluid is perfectly still, which means, by definition, there are zero tangential stresses anywhere.
That simplifies the math a lot, I imagine. It means if you're in a pool and you push your hand flat against the wall, the water isn't trying to, drag along your palm. It's just pushing straight back.
That is the exact intuition we need. Now that's shape change. What about volume change? We think of solids as basically incompressible.
Liquids are pretty close, but not quite right. We often treat them that way, but the sources bring up compressibility, which they measure with this term, kappa.
Yes, capacities. And you're right, liquids are incredibly stiff compared to, say, a gas. But they do respond to pressure, which we'll call PS, with a change in volume, delta V day. And the relationship is pretty straightforward. The fractional change in volume is just minus kappa times the pressure.
So that kappa is just a measure of how squishy the liquid is.
How squishy it is, exactly. For water, that value is tiny, but it's not zero. And it matters when the pressures get absolutely enormous.
I remember seeing something about this. The water at the bottom of the Mariana Trench is actually measurably denser than at the surface because of the immense pressure. It's something like 1,000 atmospheres down there.
It absolutely is. The density change is real, though. It's still pretty small, less than a 5% increase, I believe.
Yeah.
So for most engineering applications, and certainly for the physics we're developing today, we make a key simplification. we treat the fluid as perfectly incompressible.
And this is our first step toward building the model of the ideal fluid.
Right. The ideal fluid is our theoretical playground where we ignore the messy parts of the real world to get to the core principles.
So, besides ignoring compressibility, what else are we throwing out?
Two big things that we'll actually bring back later.
Mhm.
First is internal friction, or viscosity. That's what makes honey pour slowly and water pour quickly.
Got it.
And second, we're ignoring surface effects. All the weird stuff that happens at the boundary of the liquid, the things that let it form, drops and bubbles.
So by setting aside viscosity and surface tension, we double down on that main consequence. For our ideal fluid at rest, all forces at any boundary are purely normal forces. And that simplification is the bedrock we need to build everything else. Okay, let's take this ideal fluid incompressible, no friction, no funny business at the surface, and put it into a slightly more complicated situation. And this is where it gets really, really cool. The classic rotating bucket experiment.
Ah, yes, the Eimer.
You take a bucket of water, spin it at a constant speed, and the surface, well, it doesn't stay flat. It does something dramatic.
It forms this beautiful, stable dip in the middle and rises up along the edges. This is a perfect example of physics in what we call a non-inertial reference frame. The frame itself is accelerating, it's rotating. But the key thing is, the water surface takes on this new shape and then it becomes perfectly static relative to the bucket.
Okay, so we need to figure out why it chooses that specific shape. Let's do the analysis. Let's look at a single tiny particle of water sitting right on that curved surface. What forces are acting on it?
So from the perspective of someone riding along with a bucket, there are two main forces on that little mass. First, you have its weight, dollars, which is just times dollars pulling it straight down.
Okay, gravity. Simple enough.
Second, because we're in this rotating system, we have to introduce what's called a fictitious force to make the physics work out. It's the centrifugal force, 5 Z's.
Right, the force that feels like it's throwing you outwards on a merry-go-round.
That's the one. It pulls the particle straight out radially, away from the axis of rotation. And its strength is, to make it know, omega dou double, R, where omega is angular velocity, how fast it's spinning, and 3 days is how far the particle is from the center.
So you have gravity pulling down and centrifugal force pulling out.
Now, here's the condition for equilibrium. For that particle to stay put on the surface, the total force, the vector sum of gravity and centrifugal force, must be pointing perfectly perpendicular to the surface at that exact spot.
Ah, because if it wasn't, there would be a component of the force along the surface.
And the fluid would flow.
It would flow. Right. It has to be perfectly normal to the surface for it to be static.
Exactly. And this equilibrium condition gives us really neat mathematical insight. The slope of the surface at any given point, which we can write as the derivative,
The change in height for a change in radius?
must be equal to the ratio of those two forces, the
Right.
vertical one and the horizontal one. So it's the centrifugal force, $70 divided by the weight, $5.
Okay, let's look at that ratio. It's omega 2 omega joy divided by mega g. The mass is on the top and the bottom.
It cancels out.
Completely.
Wait, that's a huge deal.
It's a profound result. It means the shape of that curd has absolutely nothing to do with the mass or the density of the fluid you're spinning. You could fill the bucket with gasoline, water, or even liquid mercury.
Which is incredibly dense.
And if you spin them all at the exact same rate, they will all form the exact same surface shape. The slope only depends on how fast you're spinning it and the strength of gravity.
That's incredible. So if the slope is proportional to the radius, $, what shape do you get when you integrate that to find the actual height?
You find that the height, z, is proportional to $2 squared, and a function that goes as squared is
A parabola.
an exact parabola of revolution, or a rotations paraboloid. It's the only possible shape where the combination of gravity and centrifugal force is always normal to the surface at every single point. It's just baked into the laws of motion. Such a precise, beautiful result from just spinning a bucket. But this isn't just a classroom demo. This exact principle is used in some mind-blowing technology.
Oh, absolutely. The most famous application is in building liquid mirror telescopes, or LMTs. To focus light from distant stars, a telescope's main mirror needs to be an incredibly precise parabola.
And making those traditionally involves taking a huge, heavy piece of glass and grinding it for months, sometimes years, to get that perfect curve. It's painstaking work.
And extremely expensive, especially for very large mirrors. But with this principle, you can skip the grinding altogether. Scientists take a large circular dish and pour a reflective liquid metal into it, usually mercury.
And then they just spin it.
They spin it very slowly and very, very precisely. And because of the exact physics we just worked out, that balance between gravity and centrifugal force, the surface of the liquid mercury automatically forms a perfect, flawless paraboloid.
It's like a self-polishing perfect mirror. The physics does all the work for you.
And the surface it creates can be smoother and more optically perfect than anything you could grind by hand, at a tiny fraction of the cost. The precision is just stunning. It's a perfect example of how understanding these fundamental principles of hydrostatics can lead to truly brilliant engineering.
Okay, we've seen the beautiful geometry of a fluid in motion, or at least in a rotating frame. Let's come back to a fluid at absolute rest, just sitting in a tank. We need to define exactly how pressure works. How does it transmit force?
Right. This means we have to get into the mathematical heart of it. We need to see how pressure gradients create force.
So we start small. We imagine a tiny, tiny little cube of fluid, a differential volume element we call dV-dolars.
And we know that pressure is pushing inward on all 6 faces of that cube.
Now, if the pressure was exactly the same everywhere, the same value on the left face as the right face, the top as the bottom, what would happen?
All the forces would cancel out perfectly. The push on the left would be canceled by the push on the right. The net force on that cube would be 0.
But in the real world, pressure usually isn't uniform. It changes, especially with depth.
And that's where the force comes from. Let's just think about one direction for a second, the x direction. The force pushing on the left face is pressure times area, P dot dCOTRA. But the pressure on the right face, a tiny distance away, is slightly different.
Okay, so there's an imbalance.
Exactly. And when you calculate the difference between the forces on those two opposite faces, you find that the net force in the x direction is proportional to how quickly the pressure is changing in that direction. The partial derivative, partial wax.
And if you do that for all 3 directions, x, y, and z, and add them up as vectors, you get the big result.
The crucial vector equation that governs this whole field. The net force vector on that little volume element is equal to minus the gradient of the pressure times the volume. For Rakebla, Pi got the Veilja.
This equation is so important. We should probably unpack it a bit. Pressure itself, P dollar, is a scalar, right? It's just a number, like temperature. It doesn't have a direction.
Correct. But the force it creates is a vector. It has magnitude and direction. And that direction comes from the gradient. Nalabla Pia.
So what exactly is the gradient?
Think of it like this. If pressure were altitude on a topographical map, the gradient vector at any point tells you the direction of the steepest uphill slope. It points in the direction of the fastest increase in pressure.
But there's a negative sign in the equation. Zalapitiev T do dv-like.
And that negative sign is fundamental. It means the force doesn't point up the pressure hill, it points down it. The resulting force is always in the direction of decreasing pressure.
Ah, so fluids always get pushed from high pressure towards low pressure.
Always. That's why when you puncture a tire, the air rushes out from the high pressure inside to the low pressure outside. The gradient is the driver of the force.
Okay, so that's the rule for fluid motion, but we're in hydrostatics. The fluid is static, so the net force Vegeliev must be...
0. Hashtag the hydraulic press.
Exactly. So what does our big vector equation tell us if the net force is 0 and we, just for a moment, ignore gravity?
Well, if that is 0, and the volume dvol is obviously not 0, then the only thing left is the gradient of pressure. Now, blah, Peter. That must be 0.
And if the gradient is 0, it means the pressure isn't changing. It has to be the same everywhere in the fluid.
That's the conclusion. In a closed, static fluid, pressure is transmitted instantly and equally to every single point. And this is the principle behind one of the most powerful, simple machines ever invented, the hydraulic press.
Because the pressure is uniform, the pressure under the small input piston, P$1, has to be the same as the pressure under the big output piston, P.
Which gives us the simple relationship. Force 1 over area 1 equals force 2 over area 2. F$A1 equals F2 A22.
Let's make that concrete. If the output piston has an area, say, 100 times larger than the input piston,
then the force is multiplied by 100. A small push of 10 pounds on the small piston generates a massive lifting force of 1,000 pounds on the large one.
That feels a little bit like getting something for nothing. There has to be a trade-off, right? Conservation of energy must come into play.
Oh, absolutely. The trade-off is distance. The hydraulic press is basically a force multiplier, like a lever. Work is force times distance. If you multiply the force by 100...
You must have to divide the distance by 100 to keep the work the same?
Precisely. You have to push that small piston a very long way to make the large piston move just a tiny amount. You're trading distance for force.
And that's why we use hydraulics everywhere, from a car jack to the brakes in your car to the landing gear on an airplane. It's all about force multiplication. Hashtag tag introducing gravity hydrostatic pressure. Okay, time to turn gravity back on. That uniform pressure idea was powerful, but it ignored the most common force we deal with. Let's bring gravity back, because it completely changes the game in an open system like a lake or the ocean.
Now, for our little cube of fluid to be in equilibrium, the upward force from the pressure gradient has to perfectly balance the downward force of its own weight.
And its weight is just its density times gravity is a dollar times its volume, deV dollars, and that force acts straight down in the minus c direction.
So when we set up that balance, we find that the pressure gradient in the horizontal directions is zero pressure doesn't change sideways. But in the vertical direction, the rate of change of pressure with height, partial zeta, must exactly equal minus rho times g.
Partial d tri dot ge, that's the fundamental differential equation for hydrostatics.
It's a very compact way of saying that the reason pressure changes as you go up or down is because of the weight of the fluid itself.
And because we're still assuming our fluid is incompressible, that density, the hour, is a constant, which makes that equation really easy to solve.
Very easy to integrate. And when you do, you get the famous hydrostatic pressure formula, sometimes called the barometric formula, for incompressible fluids.
Let's say the surface is at height dollars, and we want the pressure at some depth tau.
The pressure at that depth, para, will be the pressure at the surface, usually just atmospheric pressure plus an extra term, a pars g baro d zeri.
That term, d gel times the depth, is the pressure caused by the weight of the column of fluid sitting on top of you.
And the most important takeaway, the thing you feel in your ears when you dive to the bottom of a pool, is that this extra pressure increases linearly with depth. Go twice as deep, you get twice the pressure from the water.
Right, and we have to remember our first insight, that pressure acts in all directions equally. It pushes down on the floor, up on the bottom of a boat, and sideways on the walls of the container. Okay, this linear relationship between pressure and depth, it leads us straight into a really famous puzzle that just messes with your intuition, the hydrostatic paradox.
Yeah, yes. This is a classic. It's a great test of whether you've really understood the principles because it seemed to violate common sense.
So set it up for us. Imagine 3 different containers.
Yeah. All 3 have the exact same area at the bottom, and we fill them with water to the exact same height, all dollars. Vessel A is just a simple cylinder. Vessel B is a wide conical flask, so it holds way more water. And vessel C is very narrow, like a thin tube, so it holds much less water.
So very different amounts of water, very different total weights.
Dramatically different weights. And yet our formula, PP equals right air EGH plus atmospheric pressure, says the pressure at the bottom depends only on the height of the fluid, that $. It says nothing about the shape of the container or the total volume of water.
So the pressure at the bottom of all 3 containers is identical.
Identical.
So since the base area is the same, the total downward force on the bottom of each container is also identical. How is that possible? How can the skinny tube with just a little bit of water exert the same downward force as the huge, heavy cone?
The resolution to the paradox, the key insight, is that we've been forgetting about the container walls. The pressure is acting everywhere, not just on the bottom. The walls are also pushing on the fluid.
Okay, so the walls are part of the force balance. Let's take the wide cone, vessel B. It has a lot of extra water.
It does. And that extra water has weight. But look at the walls. They're sloped outwards. The pressure from the fluid pushes on those walls perpendicularly. That force has a horizontal component, but it also has an upward vertical component.
Ah, so the sloping walls are actually helping to hold up the water.
They are partially supporting the weight of the extra fluid in the wings of the container. So the bottom of the container only has to support the weight of the water in a virtual cylinder directly above it. The walls take care of the rest.
Okay, that makes sense. The walls are lifting. So what about the opposite case? Vessel C, the skinny tube. It has a deficit of water.
Right. To get the same high pressure at the bottom, something has to be pushing down to make up for the missing weight. And again, it's the walls. The walls are sloped inwards.
So the force from the pressure on the walls is pointing outwards and downward.
The walls are exerting a downward force on the fluid, adding virtual weight that gets transmitted to the bottom. The walls compensate perfectly in both directions.
That's fascinating. So if you put each of these on a weighing scale, they would show very different total weights.
Of course.
But the force on that specific circular area at the very bottom is identical in all 3 cases. It's all about the local pressure, not the total global weight of the system. Hashtag tag the principle of Archimedes.
And another direct, really important consequence of this pressure-depth relationship is buoyancy. The reason things float.
Archimedes' principle. It's one of the oldest ideas in physics, but you're saying it's just a direct result of the pressure formula we just derived.
That's all it is. Think about any object submerged in a fluid, like a submarine. The water pressure is pushing on its entire surface. Now, the pressure on the left side is balanced by the pressure on the right side, so the horizontal forces cancel out.
But the pressure isn't the same on the top and the bottom.
That's the whole story. The bottom of the submarine is deeper than the top. Because pressure increases with depth, the upward push on the bottom surface is greater than the downward push on the top surface.
So there's a net upward force.
A net upward force. And when you do the math and integrate that pressure difference over the entire surface of the object, no matter how complicated its shape, the result simplifies into something incredibly elegant.
Archimedes' law.
The buoyant force, Phi is exactly equal to the weight of the fluid that the object has displaced. Phi z, rho text, float. It's a beautiful simplification.
So if a ship displaces 1,000 tons of water, it gets an upward push of 1,000 tons. That's simple.
That's simple. And then, whether it sinks or floats is just a competition. Is that buoyant force bigger or smaller than the object's own weight?
Which is really a question of density.
It comes down to average density. If the object's average density is less than the fluid's, it floats. If it's more, it sinks.
And that's why a ship made of steel, which is way denser than water, can float. The average density of the ship, when you include all the empty air inside its hull, is much less than the density of water.
Absolutely. The physics only cares about the weight of the volume you pushed out of the way. It's a perfect illustration of how that simple, linear increase in pressure with depth creates a foundational principle of the world.
Okay, we have spent a good amount of time in this clean, perfect world of the ideal fluid. Now we have to get our hands dirty. We need to transition to the real world where liquids are, sticky, they interact with themselves. We need to look at the edge of the fluid, the surface.
This is where things get really fascinating, I think. It's all about the boundary.
And the most basic question is, why do droplets even form? Why does water pull itself into a sphere?
To understand that, you have to zoom in way down to the molecular level, and you have to think about energy. Every system in physics wants to be in its lowest possible energy state.
Right. A ball rolls downhill.
Exactly. So picture a single molecule of water deep inside a glass of water. It's in the bulk. It's completely surrounded by other water molecules, all pulling on it equally in every direction.
So the net force is zero. It's happy and balanced.
It's in a low energy state. Now, take that molecule and move it up to the surface. What's different?
Well, it still has molecules pulling it from the sides and from below, but there's nothing, or almost nothing, pulling it upwards into the air.
So it experiences a net inward pull. It's being constantly tugged back into the bulk of the liquid. This means it's in an unbalanced, higher energy state.
So it takes work, it takes energy to create a surface.
That's the core concept. Increasing the surface area of a liquid costs energy. And the liquid, like any system, wants to minimize its energy.
So it tries to minimize its surface area.
And for any given volume of stuff, the geometric shape with the smallest possible surface area is
a perfect sphere.
A perfect sphere.
Yeah.
That's why raindrops, dewdrops, bubbles. They all try to become spheres. They're just trying to get to their lowest energy state. Hashtag tag quantifying surface tension.
So we need a way to measure this energy cost. The source material defines the specific surface energy, epsilon, as the work you have to do to create a certain amount of new area.
Right. And the classic thought experiment to make this tangible is using a little wire frame, like the ones you use to blow bubbles, with one side that can slide. You dip it in soapy water to create a film.
And to pull that sliding bar outwards and stretch the film, you have to apply a force. You're doing work.
You are. The work you do is that force, $5 times the distance you pull it, delta sub S.
Yeah.
But here's the clever part, the detail that people often miss.
Mm-hmm.
How much new surface area have you actually created?
A soap film has two sides, a front and a back.
It has two surfaces. So the new area you've made isn't just the length of the bar, $$ times the distance, delta sub sigma. It's 2 times L times delta sub S.
Okay, that's a key detail. And from this experiment, we get the definition of surface tension, which we call sigma. Sigma, it's defined as the force per unit length needed to hold that film.
And here's the really nice part. If you set the work you did, the force times distance part, equal to the energy you stored in the new surface, the epsilon times area part.
The distance term, delta sub S, must cancel out on both sides.
It cancels out. And you find that surface tension, sigma, which is a force per length, is physically and numerically identical to the specific surface energy, epsilon, which is energy per area. There are two different ways of describing the exact same thing. The liquid's reluctance to expand its surface. #, the Young-Laplace equation for droplets.
So now that we have a measure for this tension, let's go back to our spherical droplet. The surface is like a stretched rubber skin constantly trying to contract. It must be squeezing the inside, right?
It is. It creates an excess pressure inside the droplet. The pressure inside a drop of water is always higher than the pressure outside. We call this the Laplace pressure.
And we can figure out exactly how much higher it is by doing another little thought experiment, a virtual expansion.
Yeah, this is a beautiful piece of physics. We imagine we inflate the droplet just a tiny, tiny bit, increasing its radius by an infinitesimal amount, delta r day. We then look at the energy balance.
Okay, so inflating it requires work. The work done by that excess internal pressure, P balls would be the pressure times the change in volume, delta V dollars.
Right. And at the same time, by expanding the droplet, you've increased its surface area. And we know that costs energy. The change in surface energy is just epsilon times the change in area, delta A vel.
So you just set the work done by the pressure equal to the energy cost of creating the new surface.
You set them equal. The change in radius term, delta, cancels out, and you're left with the Young-Laplace equation for a droplet. The excess pressure, A vel I, is equal to 2 times the surface energy, divided by the radius. P pi A equals frac epsilon.
This is a huge result. The excess pressure is inversely proportional to the radius.
Yes, and the consequences are enormous. It means the smaller the droplet, the sharper its curvature, and the more massive the internal pressure becomes. A tiny little fog particle just a few microns across is under immense internal pressure.
Which makes it really hard for that particle to grow, I'd imagine.
Incredibly hard. This is fundamental to meteorology.
Yeah.
It's why cloud formation is so difficult. For water vapor to condense into a brand new tiny droplet, it has to overcome this massive Laplace pressure. That's why it often needs a seed, a little speck of dust or salt to condense onto to get started with a large enough radius.
And we can't leave this without mentioning the classic puzzle. A soap bubble versus a water droplet.
Ah, yes, the factor of 2. A water droplet is a sphere of liquid with air on the outside. It has one liquid-air interface.
So the formula is pp fractive epsilon.
But a soap bubble is a thin shell of liquid with air inside and air outside. It has 2 surfaces, an inner one and an outer one.
So you have twice the amount of surface tension trying to crush the bubble.
Which means you need twice the internal pressure to hold it open. For a soap bubble, the formula is Tp for epsilon it's up. It's these little details, governed entirely by the geometry of the interfaces, that make fluid physics so rich.
Okay, so we've moved from droplets floating in space to the reality that liquids usually touch things. Water in a glass, rain on a window. This introduces a whole new level of complexity because now you have competing forces at the boundary line.
Exactly. When a drop of liquid sits on a solid surface, you get what we call a 3-phase boundary. You have the solid, the liquid, and the air all meeting along a single line.
And since every type of surface has an energy cost, we now have 3 different surface tensions all pulling on that junction point. It's a microscopic tug-of-war.
It is. You have the tension of the liquid-air interface, sigma, which we just talked about. Then you have the tension of the solid-liquid interface, sigma Ballersner. And finally, the tension of the solid-air interface, the drywall.
And those 3 forces are all pulling, trying to minimize their own areas, and that junction point will slide around until the horizontal forces are balanced.
That's right. And the balance of those forces is described by the Young equation. What it tells us is that the final angle the liquid surface makes with the solid wall, the contact angle, phi t, is determined entirely by the relative strengths of those 3 tensions.
So the angle is just the outcome of that tug-of-war.
It's the final truce. The math is sigma plus sigma cosat phi.
Okay.
You can see the cosine of the angle right in there, linking the geometry to the forces. #, wetting versus non-wetting Benezone.
And this relationship leads to the 2 very different ways liquids can behave on a surface, wetting and non-wetting.
Let's start with wetting. This happens when the solid surface really wants to be covered by the liquid. In energy terms, the tension of the drywall, sigma, is very high. The system can lower its total energy by replacing that high-energy solid-air interface with a lower-energy solid-liquid interface.
So the liquid spreads out to cover as much of the solid as it can.
It creeps up the wall. You get a concave meniscus, and the contact angle phi is small, less than 90 degrees. Think of water on very clean glass, or how a paper towel soaks up a spill.
Okay, so what's the opposite? Non-wetting.
Non-wetting is when the liquid molecules would rather stick to each other than to the solid surface. The adhesion to the wall is weak, but the cohesion within the liquid is strong.
So the liquid tries to minimize its contact with the wall.
It pulls back on itself, forming little beads or droplets. This is what we call beading up, like water on a freshly waxed car or waterproof jacket. The contact angle is large, greater than 90 degrees.
A classic example is mercury on glass, right? It forms almost perfect little spheres.
A perfect example. The cohesive forces in the mercury are so strong, and its adhesion to glass is so weak that it just balls up to minimize contact. We call these surfaces hydrophobic. #HAG capillarity.
And this whole idea of wetting, of the liquid creeping up the wall, leads directly to one of the most amazing effects of surface tension, capillarity.
This is when a wetting liquid, like water, in a very thin tube, a capillary, spontaneously climbs up the tube, seemingly in defiance of gravity.
Which seems to break our hydrostatic pressure rule, right? The water level inside the tube is higher than the level outside.
It seems like it, but it's not breaking the laws of physics. It's using one part of physics surface tension to fight another, gravity. Because the water is wetting the glass, the meniscus curves upwards at the edges.
Okay.
That upward curve means surface tension is pulling upwards along the entire line of contact, the whole inner circumference of the tube. It's like millions of tiny hooks pulling the water column up.
So the total upward force is the surface tension, sigma, multiplied by the circumference of the tube.
Exactly. And that upward force lifts the water column higher and higher until its weight.
Until its weight perfectly balances the upward pull from surface tension.
Equilibrium is reached. The upward surface force exactly equals the downward weight of the lifted water column.
And when you solve that force balance, what does it tell you about how high the water can rise?
You get a very clear result. The height the water rises, dollars, is inversely proportional to the radius of the tube, $2.
So dollars is proportional to 1 over $2.
Which means the thinner the tube, the higher the water climbs. If you cut the radius in half, you double the height of the capillary rise. This is why the effect is so dramatic on microscopic scales.
And this isn't just a lab curiosity, this is how life works.
This is how almost all terrestrial life works. Plants have incredibly thin tubes in their stems called xylem. The radius is microscopic. And because the radius is so tiny, the capillary forces are strong enough to pull water all the way from the roots up to the leaves of the tallest trees on Earth, fighting gravity every inch of the way.
So the existence of a 300-foot-tall redwood tree depends on this tiny contact angle, this molecular tug-of-war happening in a microscopic tube.
It's a masterpiece of natural engineering, driven entirely by the fundamental physics of hydrostatics and surface tension. #outrip.
Okay, let's take a step back and look at what this all means. This has been a huge journey. We started with the most basic definition of a fluid, the simple fact that it can't resist shear, and ended up explaining how giant telescopes work.
Right, that beautiful parabolic shape of a spinning liquid. We also figured out the core of hydrostatics, the pressure gradient, and used that to see how a hydraulic press can multiply force.
And we finally resolved the hydrostatic paradox, showing how the walls of a container always conspire to make sure pressure only cares about depth, not about the shape or the total amount of water.
Then we dove into the real world of surfaces. We derived the Young-Laplace equation to see why tiny droplets are under such immense pressure, which connects directly to how clouds form. And we finished with capillarity, seeing how that same surface energy allows the entire plant kingdom to drink.
It really is an elegant and complete picture. And a key part of that picture was establishing that for an incompressible fluid, like water, pressure just increases in a straight line with depth. That simple barometric formula, rho patella g p tail g dot g h g a z.
We applied that to the ocean, where density is pretty much constant. But what happens if you apply that same idea of hydrostatic balance to a fluid that is very much compressible, like our own atmosphere?
So the density is no longer a constant in that equation. It changes with altitude.
It changes dramatically. As you go up, the pressure drops, which allows the air to expand, which makes it less dense, which in turn changes how fast the pressure drops. It's a feedback loop.
So it wouldn't be a straight line anymore.
Not at all. So here's something for you to think about. Considering the atmosphere is compressible, how would that pressure height function change from our simple linear model? What kind of curve would it be? And what would that new, more complex relationship tell us about where the top of the atmosphere really is and what drives the massive movements of air we call weather?
A great question to leave us with. Until next time.